Hi everybody, we are going to do a lecture on a little bit of atomic history, so I'm going to do a history lesson today. We'll go through some of the important discoveries of how we came to today's model of the atom. So we're going to start on paper. I do have some demos and things for you today, a couple little things to show you, a couple things on the computer. So let's go ahead and get started. And we can entitle this, I don't know, just atomic history. So that should be a capital H. And we're going to start a long time ago in a galaxy far, far away. And we're going to start with the ancient Greeks. It was about 400 BC. So way back in the ancient Greeks, we're talking about people like Aristotle and Empedocles and Democritus and Leucippus. So these were all ancient Greek philosophers. And you think way back to 400 BC, they really had no scientific equipment. They were really just thinkers, and they were some of the first people that looked at the things, looked at objects in their environment and tried to come up with ideas of how those things were made. And so they came up with some really basic ideas without doing science. They didn't have any equipment, they weren't doing experiments or anything like that, but they came up with some pretty good ideas, right, without using any scientific experiments. Right? So for example, the Greeks came up with the idea that matter is composed of four fundamental substances. Matter is made up of four fundamental substances. And the four fundamental substances they thought were fire, earth, water, and air. So the idea was that all matter was made up of these four things in different combinations. So the idea was, hey, look at this stool is made up of fire, earth, water, and air. Okay, now, this probably would be considered to have a lot of air in it. Okay, they would have thought it would be very little air. Right? There would have been a lot of earth because it's hard. Right? How about water? Well, it's wood, you know, and they knew that you cut down a tree, there's water inside of it, so it has some water in it. Right? How about fire? Is there a lot of fire in this? Well, wood burns, so their idea is, well, look at it. If it burns, it's giving off that fire that's got to be inside of it. Okay, so the idea way back then was that everything was made up of four basic substances. Now, they weren't right about those four basic substances, okay, but the idea that matter is made up of of something is correct. Okay, but they were just wrong with what it was made up with. Okay, so we now know that all matter is made up of 118 elements. Okay, one of the 118 elements, either in different combinations or in compounds, that kind of stuff. Okay, so the idea, though, that matter is made up of some fundamental part started way back with the ancient Greeks. The second idea was the idea of the atom. The idea is that there's a piece of matter so small it cannot be broken down. So the idea is this, okay? If we were to take this steel sphere and cut it in half, and then cut it in half, and then cut it in half, and keep cutting it in half and cutting it in half, eventually we would come to something that couldn't be cut in half again. And that something is what makes all matter up. They didn't know what that something looked like. They didn't know what that something, how big that something was. They had no idea what that something was, right? But they came up with the idea that that something is what makes all matter up, which is the idea of the atom. And so way back in 400 BC, we already had the idea that atoms make everything up. Well, after the Greeks, the next biggest thing that really happened were the alchemists. And alchemists were actually called pseudoscientists. Or they did pseudoscience. So, in Europe, kind of coming out of the Dark Ages, and even in the Dark Ages, Dark Ages there was not a lot of scientific research. The church ruled, and if you disobeyed the church, basically you were excommunicated, you were dead. Right? So any type of scientific research was frowned upon by the church, and most of the scientific research during the Dark Ages basically stopped. Okay? There was no scientific thought, or very, very, very little. Okay? Until we started coming out of the Dark Ages, and these alchemists started to pop up around England, and they were people that claimed stuff like they could turn lead to gold, they could take any base metal and turn it into gold or silver, stuff like producing the elixir of life, okay, which made you live forever. The sorcerer's stone was actually something that people claimed. Those are real things that these alchemists claimed that they could do. Okay? Now, they never were able to turn lead to gold. They were never able to do that. They didn't make some drink that made you live forever. Okay? But they did do, or they started to bring society back into science. They didn't really do science, but they did some pretty important things that they did. So some of the alchemists, what they did is they discovered a lot of the elements. They actually made a lot of the first chemical equipment. They made a lot of that first chemical equipment. They like a mortar and pestle. Okay? They did some of the first distillations. Right? So they started to create some of this equipment that we still use today in science. And then they started to learn how to make different compounds. So they started to make some specific compounds, and actually, they were the ones that really started to make our first acids. Okay, and that was pretty important. Right, so the alchemists weren't doing real science, but in their just putting stuff together, they discovered a lot of important things, and they started to bring this scientific research back into society. Next, we have a man named Robert Boyle. Actually, Boyle was an alchemist. And Mr. Boyle, he actually did stuff with gases and probably remember Boyle's Law and stuff like that. So he worked with a lot of different things. But Boyle defined what an element is. a simpler substance. Okay, so these are just all basic ideas that we're slowly working towards to build our model of the atom. As we went through time, right, a little bit after Robert Boyle, we get Lavoisier. Lavoisier. And he was a pretty important person. So he's actually considered the father of modern chemistry. So he's kind of the person that's given credit for turning the alchemists and going from that pseudoscience into actually a real science. All right, so he went from a qualitative type of science where we're making all observations with our senses to more of a quantitative type of science. And we're actually measuring things and doing calculations. And he's kind of giving credit for that. So that's one of the big things he did. So he changed chemistry from qualitative to a quantitative science. He also played a major part in the development of the metric system. He actually started putting together a lot of the different research that had been in the past, not research, but stuff that the alchemists has done, and people that had a lot of different research, and he produced the first list of elements. And he started to organize them, but he's not given credit for that periodic table, but he starts to produce a very extensive list of the elements. One of his biggest discoveries. He discovered that matter may change shape or form, but mass remains the same. So we can change matter, we can change it into different forms, we can change its shape, okay? But the mass remains the same. This is the beginning of the law of conservation. So our law of conservation is extremely important. Okay? Matter and energy cannot be created. Actually, matter, energy, and charge cannot be created or destroyed. It can be converted into different forms, all right, but it cannot be created or destroyed. All right? So this is where the law of conservation started. Number 5. This is Joseph Proust. And this is, you don't need to know dates, but early 1800s. And he comes up with another law, and this is called the law of definite proportions. And the law of definite proportions says a given compound always contains the same proportions by mass of each element. So because of the definite proportion, law of definite proportions, if we look at H2O, okay, every time that we see an H2O molecule, right, we have 2 hydrogens and 1 oxygen. Okay, so the mass of each of the hydrogen is 2 and oxygen is 16. Okay, so this is always the same in a compound. Well, all of these guys were slowly developing ideas that we needed for our first model. And that brings us to John Dalton. And he worked in early 1800s, okay, and he developed the first atomic theory, 1803. He kind of put everyone's work together. To make the first atomic theory. So John Dalton went back and he looked at what the Greeks had written. He looked at what the alchemists had written and went through a lot of what they had found. You know, he looked at Proust and he looked at all these different things, and he was the first person to kind of solidify into this first idea of the atom and what it looked like and how it acted. And this was a huge step. And you need to know his atomic theory. So, first thing says, elements are composed of very small particles called atoms. So he takes this idea of an element and the stuff from the Greeks, and he calls this particle that makes everything up the atom. He also says that atoms of the same element are identical. And atoms of different elements are different. So let's talk about that for just a little bit. So John Dalton's idea of the atom was that it was a solid sphere. Okay, now obviously this is way bigger, but he said it's an extremely small piece of matter, it's a solid sphere. And he said that atoms of the same element are always exactly the same. They have all the same properties. So if I have 2 gold atoms, those gold atoms are the same, exactly the same in every way. Same color, same density, same melting point, same boiling point, same. Okay, so if I have 2 atoms of the same element, they're exactly the same. He also said that two atoms of different elements are very different. Now they're all solid spheres, but they have very different properties. So let's say we have a gold atom and a silver atom. Well, the gold atom is gold and the silver atom is silver. They have different melting points, different boiling points, different masses, different. Okay. Atoms of one element cannot be changed into a different element. So he looked at all the alchemist research and what they claimed to do, and found that they were never really successful. No one was able to turn lead to gold. So in his atomic theory, he said, look, there's no way. Okay, an element is what everything's made up of. Okay, we can't take one element or one atom and turn it into a different element. That's impossible. D. Chemical compounds form when two or more different elements combine. Chemical compounds form when two or more different chemical compounds combine. A given compound always has the same relative number of kinds of atoms. Always has the same relative number and types of atoms. A given compound always has the same relative number and types of atoms, and that's that idea of H2O. And it's always made of two H's and one O. The masses are always the same. Now, last thing to write for Dalton. So this is number E. His model of the atom was a solid sphere. It was a solid sphere. So all the atoms were solid spheres, okay? Just extremely small. All right, well, this was the first big step into atomic theory. Was John Dalton right? Well, yes and no. He had some very good things, but there are some things that he got wrong. So, the next person and he was kind of a disciple of Dalton, was a man named J.J. Thomson. And he was in the mid-1800s. And J.J. used a cathode ray tube . tube and found the electron. He found the electron. And up front, I actually have it. Okay, so, I don't know if you can see, but this right here is what's called a cathode ray tube, also called a Crookes tube, and this is what he used to discover the electron. And I'm going to turn the lights off. I don't know if this will work for you or not. Hopefully you can see it. I'm going to have to hold this back here. Yeah. So you can see what's happening. So if I bring this here, you can see a green line that goes across. Okay? Those are actually electrons going from the left side all the way across to the right. Okay? So electrons have a negative charge, and that's how we found them. So if we take a magnet, okay, and we place it near that string, if I bring the negative side of the magnet near the string, it pushes the string down. Okay, remember, like charges repel, so as I bring it near it, if it pushes it down, okay, we know that that's a negative charge running through there. If we turn it over and use the positive side, it actually pulls the electrons up. Okay, so the positive attracts the negative. This is what JJ used to say, hey, look, there's got to be some sort of charged particle in the atom. And he called it an electron. Okay. So this is an example of a Crookes tube. Now, Dalton didn't know anything about electrons. Okay, so his model couldn't be correct. Now, JJ was a follower of Dalton, so he still thought that the atom was still a solid sphere. But now he knew these electrons were there, right? And what he did is he made something called the plum pudding model. And he said, look, there are electrons, these negative charges, okay, stuck throughout this solid sphere. Okay, they're stuck in the matrix. So JJ changed that sphere to the plum pudding model. We still had that solid sphere, but we had these negative electrons in this solid sphere. Okay? And the matrix, this stuff around the electrons, was a positive matrix. Okay, so we had these negative electrons stuck in this matrix, and all around it, okay, we have this positive, just basic positive charge. Because the overall charge he found on this thing was neutral. So JJ comes up with the electron. Now, Millikan, Robert, this is number 8, worked with this idea of the electron. And he was in 1909. Again, you do not need to know dates. I'm just kind of giving you a little bit of background. He actually measured the charge and mass of the electron using what's called the oil drop experiment. He measured the charge and the mass of an electron using the oil drop experiment. And I want to show it to you. oil drop experiment. I hope you can see it. And this is what Millikan did. So this was in a container, all right, and these are charged plates. This plate is positive, this charge is negative, and there's a tiny, tiny hole in this positive plate. And inside here was air, and he had an X-ray source, and what the X-ray source did is it ionized and produced electrons from the air particles that were in this container. So he took some oil and he sprayed it in here with an atomizer, so the drops were tiny, tiny, tiny. And the drops went through the little hole and into this electric field. And as they passed through the electric field, they picked up electrons and got a negative charge. Okay, now gravity pulls down the oil droplets, but as they gain electrons, or when they gained electrons, okay, depending on the charge of this plate, okay, they would slow down. And if you increase this charge enough, actually the oil particles started to go back up